18, okay? 12, 18. So you have a pipe. Oh, and by the way, I hope it is clear that it measures the velocity at a specific point, right? Later on, we're gonna find out in the chapter 14 that the velocity is not the same everywhere into the pipe. The velocity is different, okay? And you kind of know that, just as a side note now, you remember the problem even in the exam, the question that I gave you. You get the two plates, or even the simple case. You have a moving plate here, and let's say there is no velocity, so there is water in between, there is liquid here. So this velocity is 0 and this is 0. Well, if both plates are 0, nothing is gonna move. But if you have this plate moving with the speed v, what's gonna happen here to the liquid?
It's gonna move.
Eh?
Velocity profile.
You have the velocity profile, which is linear. Not all the points between those two locations have the same velocity of that moving fluid. Same thing, not all the points in this pipe have the same speed. Okay? All right. So the question says, a piezometer and a pitot tube are tapped into a 4 centimeter diameter horizontal pipe. So you have a pipe with a diameter 4 centimeter. I'll just show it to you as a side profile here. That's your pipe. Okay, this is a side profile. This is the cross section of the pipe. Okay. So you have one piezometer here that measures at location 1. Actually, let me make the move down. So this distance here is 26 centimeters. And then you have the pitot tube. Okay. And this one is 35 centimeters. So it shows the water elevation in those two tubes. So the liquid in the pipe, or the water in the pipe, is V. Actually determine the velocity at the center of the pipe where those are located. Determine the velocity at the center of the pipe. Just to highlight, so that means this thing is 2 centimeters. Just to make it clear that the measuring devices, especially the pitot tube, is located at 2 centimeters.
What's that number 1? Is that just 0.1 for stagnation point?
Oh wait, why I put number 1 here?
Yeah,
No, sorry. Oh, I know why. I'm sorry, I'm looking at the solution sketch. Yeah, there is a reason why they put 1, but yeah, there is nothing there. As a matter of fact, to make it 100% correct, I'll do it like this. I'll do it at some distance. So here is the second. And there is a reason why now I'm showing you a distance. So you have the piezometer at upstream and a little bit upstream, and then you have that pitot tube with this point, which is the stagnation point. Into the water.
Your Z is going to be 2 centimeters?
The Z? No, we'll talk about it. We'll talk. Hey, yes and no. Yes and no. I mean, in general, you're right. But you will see that it doesn't matter. Remember that we're trying to find at the center of the pipe. Now, going back, something that I need you guys to pay attention. Where is the little sketch? About the stagnation point, and maybe here a little bit more clear. As this is the lines that go around this object, okay? This is the streamlines that go around this object. And you have this streamline that targets directly this point. Now, at the point of contact between this streamline and this object, at that very, the point of interaction between the streamline and the object, what do you think will be at that point of, contact, the velocity of the particle? Remember, we're talking about the point of contact. Zero. Okay, instantaneously. So keep that in mind for a second. We'll use that information. Oops. So now, let's say I don't want to use the formula for the time being. We need to prove it. So what we will do is we're going to use the Bernoulli equation. I'm going to rewrite P over gamma plus V squared over 2Z plus Z equals constant, right? We always start from this. That's the only thing that you're going to have in the exam. P over gamma plus V squared over 2Z plus Z equals constant. And I told you that this formula is applied along a streamline. Along a streamline. So let's look at the streamline. Okay, so we have this piezometer measuring something at this point. Let's call this point 1. And then you have the streamline until that streamline hits this stagnation point, which we'll call it point number 2. So now we define the 2 points and we're going to apply the Bernoulli equation, 1 and 2. From 1 to 2. You can apply the Bernoulli at any point you like, as long as it's along a streamline. The same streamline, right? That's why we're doing horizontal. Okay. So what do we have? P1 over gamma plus V1 squared over 2Z plus Z1 equals, since it is constant, so does not change along a streamline, this will be equal to what? P2 over gamma, very nice, plus V2 squared over 2Z plus Z2.
Does that change?
Eh? That is where, because that's what Christian said earlier, is equal to 2. Yes, technically, the elevation of this point is equal to what? 2. The elevation of this point?
It's equal to 2, so they
So now
cancel each
those
other out.
two can cancel, although both of them are 2.
Unless they restrict.
Now, you need to understand that the datum that you select is up to you. Now, I may have a datum further down, but it doesn't make any sense at this point. Since we have the bottom side of this pipe, let's use this as my datum. But regardless, I would like still to put here that I use this one as my reference datum. Okay, so you remember that for this class and for the next class as well. It's an energy equation, so the elevation plays a role. Here it doesn't matter because both points exist on the same elevation. So now, what is the condition of the stagnation point? What we just said earlier at the instant point in time that this hits?
0.
0. So now, one thing that you need to remember that the velocity at the stagnation point will be 0. So let's see what we have remaining. P1 over gamma plus V1 squared over 2G equals P2 over gamma. That being said, I can keep my V1 squared over 2G on the left-hand side, and I'm gonna have P2 over gamma minus P1 over gamma.